Unmute. Okay, now I'm unmuted. All right. For some reason, this is just there. Okay, great. Okay, so we're going to, this is a finish of the material from 2 weeks ago. We did a diversion last week. And so I'm going to quickly go over the same material that I did 2 weeks ago until we get to the binary erasure channel, which is a new channel that we haven't talked about, and channel capacity, and a couple of more things that we're going to cover. So we've been doing the abstract forever. All right, so as I said 2 weeks ago, logic was initially formalized by George Boole in 1815 to 1864. And although the principles had been started in the Greek era, Boole's contribution was to make this into a mathematical set of equations called Boolean logic or Boolean algebra. He was a son of a cobbler, and he was much more interested in science than cobbling. Anyway, this is what George Boole looked like. This is what Claude Shannon looked like. And this is from slightly after, a few years after he did his groundbreaking material on information theory. So for a few years, people just thought it was a beautiful and fascinating theory, but eventually everybody realized that it was really the basis of all commercial communication systems. And he gave a talk entitled Creative Thinking in 1952. And he said that the main things you need to do creativity is training and experience, intelligence, and motivation. And by motivation, he meant both the internal drive, but also a need to understand things in multiple ways, a satisfaction that you really understand all of it. He gave a number of tricks, simplification, and this became clear in his work that it was really he focused on the communication channel as opposed to the meaning that there was in information, and that simplified the problem completely. You also need to know similarity to a known problem, and he had experience with the Hartley entropy and previously, and always reformulate, keep trying to know a different way to do the same material and avoid getting in a rut. Generalized, which is the opposite of simplify, but do that later in the process. Structural analysis and inversion, work back from desired results. Okay, so be interested in several things at all times, look for contradictions as well as proofs, study what's happening in multiple fields. Don't assume that the work on many others. Don't just, I'm sorry. Study what's happening in multiple fields, but don't work on many others, on what others are already working on. Ask conceptual questions. Don't write papers unless you really need to share something fascinating. And don't assume your readers know everything. Spoon feeding is a good idea. So, as I said, his key insight was that the fundamental problem of communication is that of reproducing.
Hey, Bob, can I interrupt you to ask whoever's got the background radio on to turn it off, to mute yourself? Because it's coming through and it's kind of annoying.
Okay, are you hearing my wife's yoga class in Zoom?
Probably that's what it is, yeah.
Okay, let me go shut the door.
I was just doing all the stretching. I thought that was what we were supposed to be doing.
All right. So this is his quote: "The fundamental problem of communication," and he did not think about the meaning of messages, simply that you need to, from one point to another, exactly or approximate a message sent through a channel. And these, although having meaning, the correlation between those and the physical symbols, the semantic aspects, are irrelevant to the engineering problem. The significant aspect is that the actual message is one selected from a set of possible messages. And these are thought of as having probabilities of these. Initially, it was designed for using the postulate of equal probability, but that quickly turned out not to be very useful. And we did quite a bit of diversion last week on various kinds of distribution in English language, such as the zip distribution and digrams, trigrams, etc., and building it up to a Markov model, a discrete Markov model. So here was the system that he was talking about. Somewhere out here is the information source, and out of that information source, there's a collection of messages. One of those messages is selected, is going to be sent over a channel. The channel starts with the transmitter and ends with the receiver. So the message goes into the transmitter and gets formed from the message content in whatever symbols it represents to the signal over whatever channel there is. We've been using at least a couple of different ones. One of those is the party where Alice and Bob are talking in the middle of noise. And others have been things like the teletype where wires were literally hard connected between the two devices that were being sent the message back and forth. So the message gets transmitted, sent as a signal over some channel. There's a receiving signal, and that gets changed into the received message. So hopefully, if the transmission was accurate, the receiver is just the inverse of the transmitter. And then the received message goes on to a destination, again, a part of the system that is not part of the channel. So we have used several examples: sequence of letters in a telegraph or teletype system, a single function of time, as in a sound wave in radio or telephony, a function of time or other variables in black and white television. So this would mean a screen position X and Y as a function of time. And the light intensity is to be shown on the tube plate. Several functions of several variables would be needed in order to do color television, because you need red, green, and blue. And so you can think of this as a vector field over the same positions and time. Various combinations, of course, can also be created. So a transmitter which operates on a message in some way to provide a suitable signal for transmission over the channel. In telephony, this usually means just changing the sound pressure into a proportional electrical current. In telegraphy, there's an encoding operation which produces a sequence of dots, dashes, spaces, or various holes in a tape, whatever is the system that we're dealing with. The initial kind of digitization that was done at the time of the Bell system was the multiplex PCM, pulse code modulation. And the signals were regularly sampled at a uniform interval, and each one was quantified. So this has the picture. So this has been limiting to 4 bits in the discretization, and the PCM approximation shows where it comes to the closest value that it can here. When it's equal like this, they're usually randomly chosen. This one happened to choose above to 8. And then at the next one, it's virtually exact at 9, a little bit off at 10. Then we go to 12, and we're a little less at 12 than we need to be, etc. And it keeps going around as we do this. So you take a point on the curve and you approximate it, in this case, simply to numbers between 1 and 15, or actually between 0 and 15. And then those are recreated afterwards using a methodology called bandwidth interpolation. So the channel is merely a medium used to transmit the signal from transmitter to receiver. As I've said, it could be a pair of wires in a teletype, coaxial cable, band of radio frequencies, beam of light, whatever. During the transmission or at one of the terminals, the signal may be perturbed by noise, either during the transmission or at the either end of the terminals, the transmitter and the receiver. And the previous picture showed how that works. And the receiver ordinarily just does the inverse operation, as I've mentioned, and the destination is the person or thing or device such as TV, whatever, that the message is intended for. So we want to represent various elements involved in the mathematical entities and the suitable idealization from their physical counterparts. So you have to make a mathematical model for what the physics of the process actually works. And these communication systems can be categorized roughly into discrete, continuous, and mixed. And by a discrete system, I mean one in which both the message and the signal are a sequence of discrete symbols. Continuous system is one which is, although it may be discretized, is considered as being a continuous function. And as I said, the in-between values are used bandwidth interpolation. Okay, and of course a mixed system is a combination of the two. We've been talking about our process. The receiver, Bob, learns a value of an output B. Alice has sent some answer to his question, and he gains a certain amount of information. And this is the entropy of his message. This still leaves something left over. He doesn't know all about A. If he did, he wouldn't need to ask the question. So obviously there has to be a difference in the experience of the two people, and otherwise you wouldn't think that the information being sent was useful. So since he doesn't know what Alice's answers are, we have to consider his conditional entropy, that is, his the entropy of his probabilities of Alice's answers given his possible answer, his possible messages heard. So there is also some ability to not learn about the transmission. We talked about that in the future material about because there is a lot of noise. Yeah?
No, it's not critical.
Oh, okay. Okay, so the information that the receiver does not learn about the transmitted message is the measure of the failure to communicate. So this is the conditional entropy is sometimes called the equivocation of the message. It tells us how much Bob isn't sure about Alice's answers, even when he knows the received message. And that's due to either distortion or it's due to noise, whatever is the reason. He gets a message, but he still is unclear about what Alice said. And the difference between the entropy of the answer he got minus the conditional information is the mutual information. And that's the key tool used throughout communication systems, is mutual information. So this is a structural picture of what we're talking about. So there is here, over the entire region, the information, the entropy of the relationship of the received message to the sent message. And this is, of course, across all possibilities. So this is the entropy over the sum of all the probabilities. So it's the sum of the entropies of each of the probabilities in the joint probability distribution. You can, of course, always do the marginal calculation, and that gives you the probability of A, this whole circle. And of course, the entropy of that probability is H of A. Then you can similarly, for all of B, find the marginal distribution on the answers. The two conditional informations that we've been talking about, the equivocation, is this red section. This is the entropy of A given B, and this is the entropy of B given A. It's the blue section in here. And then the mutual information is about where the probabilities are the same. That's where the actual message transmission occurs, is in that region. So I've already just described all of the things that are being talked about here in the picture previously, so I'm going to move on. These are all, of course, rather abstract concepts, so I hope that if I use a simple example, it'll make it more clear. So suppose the input A is a bit. We've been talking about a question that was given to Alice that she would be able to say either yes or no, or 0 or 1 or whatever. The possible messages initially, at least from Bob's point of view, or there'd be no reason that he'd be asking Alice, is that he doesn't know. They have equal probability, 1/2, 1/2. The output is also a bit. So the output might not agree with the input, but it might flip, might change the opposite value as we went along the way.
So, Bob, let me just ask you a quick question.
Sure.
I want to get things straight here. H of A is the entropy of the information that Alice is sending.
It's the entropy from Bob's point of view, Bob's experience, not Alice's experience. Alice, if you had Alice's experience, it would be very different, because unless there's a pretty stupid reason for asking the question, you must have some prior belief that Alice has a different probability distribution than you do. In fact, you must, in the way we've been structuring it, we're assuming she knows with perfect certainty that she knows the answer. And so her entropy is 0.
Right.
But
Now,
Bob doesn't know what answer she's going to give. So he has a prior probability of H of A, his probability about Alice's answers. And since he's completely in complete ignorance, they're 1/2 a 1/2, and therefore H of A is 1 bit.
Okay, that clears it up.
Okay.
So H of A, the key for me there was that refers to Bob's prior knowledge of what
Yeah,
Alice
the communication system is always uses the information about the channel from the receiver point of view. The
Okay.
assumption that the receiver doesn't know the information coming out.
Good.
Okay. I think I've just talked about this. This is one of our first systems, our first channel, the symmetric channel. So Alice could either say a no or a yes, a 0 or a 1. And there is some probability that due to the noise in the party or whatever, the reception of a no is a yes, and that probability is E. Obviously, the probability that it gets the correct no answer is 1 minus E. So 0 to 0 is 1 minus E, and 0 to 1 is E. And it's symmetric because flipping the 1 to a 0 has the same probability, and the probability that the 1 goes to a 1 or the yes goes to a yes is also 1 minus E. So this is a symmetric channel with error probability E. So the probability that the input 0 will yield the output, I'm sorry, I have people's faces in my, okay, yes, all right, they're 1 minus E, while the probability that it flips is E, and so on. So we just discussed all that in the picture. So it's called binary because of the inputs and outputs are just binary digits. Symmetric because the errors are the same whether the input is 0 or 1. Okay, so in our example, Alice A gives an answer A, which is either yes or no, a 1 or a 0. B is what Bob thinks he hears, but it might be the same as what Alice says. There's some probability E that he hears it wrong, and the error probability is determined by the level of noise at the party. Oops. So what about our entropies? This is again from Bob's point of view. So the entropy of the input is 1 bit because Bob doesn't know the answer that Alice is going to give. And he also doesn't know the answer that he's going to hear because they're both the same for him. And the entropy, therefore, for the received message is also 1 bit. The joint entropy is a little trickier, and we took our diversion last week and we did all of the calculations associated with the calculation of the joint entropy, the mutual information, the conditional entropies, all of those things we calculated last week. So the joint probability, you have the signal from Alice, either a 0 or 1, and her states are the ones going down. And the probabilities can, or that are useful from Bob's point of view. Remember, all of this is from Bob's point of view. So the probabilities of Alice's possible answers, again, are half a half. And the probabilities of the messages that he's going to hear are also a half a half. And the joint probabilities are 1 minus E over 2 and E over 2. And the over 2s are because you have to sum over to the marginal distribution. So since this gives a half, you have to add this to this, and that has to equal to this, and similarly for that. And same thing going this way. So that's how you get a marginal distribution. Take a joint distribution and sum over the rows and over the columns. So the joint entropy is, we've been using H for 2 different kinds of symbols. One is a generic entropy due to an error E, and the H of AB is the entropy of the joint probability distribution of A and B, that is B's joint probability. When you compute that, which we did last week, you wind up with 1 plus H of E, where H of E is just minus E log base 2 E plus 1 minus E log base 2 of 1 minus E. So the result is as shown in the picture. And the binary entropy function, the H of E, is symmetric because up to P equals a half, once you go over a half, P and 1 minus P can be swapped back and forth and you get the same result. So when you take a look at the picture, you get this symmetric picture, which has a maximum at the probability E of a half, and it gives you the entropy here, where P is E and Q is 1 minus E. So when the 2 messages from the binary source and the received binary source are equally likely of error, that is, the entropy will be 1 bit. So you can run the 2 cases. You can start it with E equals 0, in which case the message is certain. Obviously, no errors occur whatsoever. Similarly, if you go to probability of 1, it's also certain. So probability at either end will always have an entropy of 0. In either case, either perfect probability or no probability, then either case there can be no surprise. And
Question, Bob.
yeah,
Quick question. Back in your diagram of the symmetric channel, the probability of a pure communication, perfect communication, was 1 minus E.
right.
So if E is 0.9, there's only a 10% chance that a 0 will go to a 0 or a 1 will go to a 1. So shouldn't it be E is, a good channel would be one where E is low, not
Well,
0.9.
actually, we're going to talk about the case, what about where it's perfect error, where every time it sends a 0, it sends a 1. Somewhere in my future slide, I'm going to talk about that. And Shannon would tell you that because there is an agreement between Alice and Bob about the nature of the channel, they would, if there was perfect error, that is, it always flipped from 0 to 1, they'd both know it, and Bob would be able to use that information to, every time she sent a no, he'd hear a yes in his mind. He'd switch it to a no. And if she sent a yes, he'd get a no. And in his mind, he'd switch it to a yes. So either no error or 100% error are equivalent to a perfect channel. They
Okay,
both
thank you.
work equally well.
Yeah, I understand mathematically it works equally well. I was just quibbling with the labeling in your slide, following the one you're showing now, where you said, how about a pretty likely? And I would have sort of thought that would be an E equals 0.1 as opposed to an E equal 0.9. I mean, I understand that you can get the same amount of information if you understand it's an inverse system as opposed to a positive system.
Yeah. Okay. Anyway, so if there's a 0.9 error, then, or a 0.1, either one, they're symmetric. So the amount of entropy is 0.469 bits. So that's almost a half a bit. So you go from 0.5 probability to 0.9 probability, or from 0.1 probability to 0.5, either way. And you wind up only getting a half a bit of results, not 9/10. And that's one of the things that you have to remember, that this type of measure is not linear. So it's additive, but you can't think of it as being, you know, if the probability changes from perfect uncertainty 0.5 to a certainty of error of 0.1, or a chance of getting the proper answer 0.9, you only gain a half a bit of entropy. So you need a lot more work in order to get certainty. Okay, so we've done the calculation, comes out 0.69, almost a half a bit. So the joint entropy, which is 1 plus that, we can find all of the other parts in our diagram. So we did this calculation last week, and so the joint distribution is 1 plus H of E. The conditional or relative entropy is H of E and 1 minus E, and it's symmetric in B and A. And the mutual information is 1 minus H of E and 1 minus E. So the joint is 1 plus h of e, but the mutual information, the amount of information actually being sent across the channel is the mutual information, and it's 1 minus h of e. So if you had 0.1 error, it would only have a little more than a half a bit being sent over the channel. This is part of the reason that we need to learn eventually very much about error correcting.
So what's an intuitive way of thinking about the mutual information?
Well, it's the amount of information that the channel gives from Alice, whatever Alice puts in to the responses that Bob is going to get. So it's the amount of the conditional information is called the equivocation of the message. So this is the amount of the message that is sort of lost in the process due to the noise. This is the amount of the message that is transmitted to Bob.
So if I set epsilon to 0, a perfect transmission system, then this mutual information would be 1.
Right. And so you would get exactly the result that you want.
What's confusing me is that a 1 suggests equal a priori probabilities.
Well, that's again, this is, remember, the communication system properties from Bob's point of view. So it's an average over what Bob knows before the message is sent.
Okay. So he doesn't know anything.
Yeah, initially his h of a and h of b is both 1. Initially, that's the reason he asked her a question, because he wanted to learn something.
Now, if epsilon is a half, that goes to 0, right?
Right. So if there's complete distortion, that is, every bit that she sends a yes, there's a half probability that it'll be a yes and half that he'll hear a no. If that's true for every time she repeats, then yeah, he'll never be able to figure out what her answer is. So yeah, the amount of information being transmitted will be 0 in that case.
I see. Okay, thanks.
Sure. So here are the properties. So the mutual information can be either h of a minus h of a given b. So the marginal entropy minus the conditional entropy, or the equivocation. And similarly, it's symmetric. So it can be h of b minus h of b given a. The definition usually given is the entropy of A plus the entropy of B minus the entropy, the joint entropy. It is symmetric, and the information of A from A is the self information. And this is, of course, all from Bob's point of view.
And this is only in the case where we have a symmetric communication channel, that is.
Yes, absolutely. This is all about the symmetric channel, and only about the symmetric channel. We're going to we're going to have a different kind of channel fairly shortly, and it'll have a different way to calculate the results. Okay, so again, these are all the things that we did and calculated in the diversion last week. So the joint entropy is 1 plus HV. The mutual information is symmetric, and it's 1 minus HV. H of A is 1, H of B is 1, H of A given B is H of E, and H of E is, again, minus E log of E, and minus 1 minus E log of 1 minus E. So these are all the things for the symmetric channel. We've now start with I of A colon B, the mutual information of A and B. And one of the things we said was that it was H of A minus H of A given B. And putting in the results from the previous table, H of A is 1, H of A given B is H, and the computation we said was 1 minus H of E, and therefore it equals 1 minus H of E, so it's true. Now, we've also said that you can do H of A, the mutual information of A and B is H of A plus H of B minus the joint entropy. Putting in H of A is 1, H of B is 1, the joint is 1 plus H of B, and therefore the two ones cancel, and we get, again, that the definition we calculated as 1 minus HB turns out to be the same 1 minus HB. So all of the same ways of doing it provide the same results. Just, you don't have to take my word for it. Okay, so the first type of channel that we've talked about is the symmetric channel with error. And just to make sure that we've said exactly what's going on, anything Alice says is exactly, if we choose a limiting case, an effective 0 error, anything Alice says is exactly heard by Bob. And in this case, the output exactly reproduces the input channel. So the mutual information, the amount of message per bit being received is 1 bit. So for every bit sent, you receive 1 bit. That's what the mutual information is all about. Now let's consider a different weird situation. Alice and Bob are not just standing near each other in a room, but they're communicating through some other machine. And the machine distorts the words that are said. In fact, whenever Alice says no, it comes out sounding like yes, and vice versa. We've talked about this once before. And in this situation, the error is 100%. E is 1. The computation for the mutual information, however, is also 1 bit. This is where I was talking about it being the case in the future that I was going to talk about. Well, I'm talking about it again now. So Bob hears exactly the opposite because of the distortion. So how does the 100% error provide the same mutual information? Shannon, again, as I discussed it previously, we've said that the communication channel has been measured in the lab. That is, Alice and Bob have a common understanding of how their communication channel works. So they know the value of E. So in the situation where Bob has the distortion machine, he knows that if he hears yes, he can just say, oh, no. She must have said no. And he corrects the results. And by exactly flipping whatever she says, he gets exactly the right answer every time. So information is about the distinction between messages, not how those messages are. This has obviously got a line that goes underneath, but it's not about what those messages are that are received. So it's the distinction between messages, not necessarily the content of those messages. All right, I've been focusing on a party example, noise and voice over a party. I want to use a different kind of a channel. I want to use a true false test as a different example here. So we're going to talk about a different kind of channel now. So I give 100 yes/no test to Lee Gale and Steve Bottle. How do I pronounce your name? I apologize.
Batil.
Batil. Okay.
Batil, just Batil.
Batil. Okay. So both Lee Gale and Steve get the same test. Now, Lee Gale knows the exact answers to 90 of the questions. However, Steve, on the other hand, thinks he knows 100% of the answers, but he only gives true answers 90% of the time.
It frozen somewhere?
Pardon? I'm sorry, what did you say?
Everything went blank. I could hear nothing.
Oh, yeah, the system just put up a bulletin that said that the connection is unstable, so I apologize. All right, so Lee Gale knows exactly 90 of the 100 questions. And she knows that she doesn't know the other 10. Steve, on the other hand, thinks he knows all 100, but only about 90% of each of those answers is actually true. So would somebody give me a way to talk about the difference in the uncertainty that can be shown in their answers? I'm taking that it's a no.
So Lee Gale will get 10% of them wrong, but Steve will get a much larger percentage of them wrong, at probably about 90% of them wrong.
No. This is, he gets 90% right. He only gets 10% wrong.
Lee could guess Lee could guess for 10 of hers, so she should get 95% right. I would get about 90% right.
Well, that would be one way to do it, but we're going to talk about a an extended channel called a binary erase channel, and we're going to use the distinction by allowing Lee Gale to have a third output called unknown. Okay, so we'll use two different channels. On Steve's, because his answer is always, an error of 10%. So we'll use a symmetric channel for Steve, but we'll use this third output that allows Lee Gale to say, okay, this is true, this is false, this is true, this is false, this is unknown. And so she will provide not only the information of what's true, but also the information what she doesn't know, which Steve, because he thinks he knows everything, obviously can't give the fact that he's giving some wrong answers. So from Steve, because he's using the symmetric channel with error 0.1, we know that each one of his answers has a mutual information of 0.531 bits. So over the 100 questions, Steve gets 53.1 bits of mutual information sent to me through the channel. So using information theory, because he gets a 53.1, I have to fail Steve. His score is, less than 70%. So anyway, it's less than 60%. So he's going to get a fail. Lee Gale, on the other hand, uses a different channel. She either says yes or no, and the answers are exactly correct. So treating these two channels, the answers that she gives exactly correct are identical to a symmetric channel with E equals 0. So, so Lee Gale summed over the 90 correct answers is 90 bits of mutual information. On the other hand, we have this unknown channel, which means that the error is essentially a symmetric channel with E equals 0.5. And each of these answers get 0 bits. So Lee's total scale is 90 out of 100 bits, or an A minus, as opposed to Steve, who has to fail. So I'm not sure that if I were actually teaching that kind, I could explain this to most students. But from the point of view of the information being transmitted, the nature of the transmission is critical to the scoring of the answers. In the binary symmetric channel that Steve uses, he only gets 53.1 bits of information across to me, and it means I need a lot more work, a lot more bits of information to send to Steve what his incorrect answers were. On the other hand, because I'd have to actually literally reproduce the correct answers for all of the 100 questions. However, in the binary erasure channel, like Lee Gale's answers, the errors are self-announcing, and I only need to send 10 bits of information for the answers that she self-announced as not knowing the answer to. So I have to send almost more than 45 bits of information to Steve to correct his answers. But for Lee Gale, I only have to send 10 bits of information. So the binary erasure channel provides much better information, mutual information, than the symmetric channel. Is everybody clear about the difference here?
No, I'm confused as heck. But quick question, does that mean a priori you know the answer?
Sure, I made up the question.
Okay, so you knew the answer. So a priori, you knew I was guessing at every answer with some, you know, some level of confidence, 90% confidence, where Yale knew the answer every time. And that is because every time you got the correct answer, it was correct. And every time you got the unknown, you just said, okay, I know that she just doesn't know that the 10 times is. So it's based on an a priori knowledge you have of the answer, of what the output's supposed to be.
Right, and due to the choice of channels. The fact that Steve thinks he knows the truth about every answer means he has no ability to use a binary erasure channel. He has no ability to say, I don't know. As opposed to Lee's. So it's a combination of two things. One, that I know because I created the test, but also because they're using two different channels. Lee Gale is using a channel that says, all right, there's three possible outputs. One is yes, one is no, and the other is unknown. And when they're yes or no, I know they're 100% accurate. And of course, I would, I have to assume that that's true to begin with, but once I got the answers from the test, I would be able to verify that in fact, she has in every time given a yes or a no appropriate into the answers. Whereas with Steve, he thinks he knows everything, but he keeps making mistakes. So he's using a different channel. He doesn't announce that his errors are self-announcing. He thinks he knows the correct answer every time. So it's a combination of in the case of the symmetric channel, even though it's got the same number of errors, it only has 53 bits of information transmitted, whereas in the binary erasure channel, even though again it's only 90% of the answers correctly given, because the errors are self-announced, the total number of bits of information transmitted is 90 bits.
Very interesting.
Yes, yes. So sorry, Steve.
No, that's all right. I must admit, I don't know everything, but this does make some sense. You did get 90 correct answers from Steve, right?
Oh yeah.
Yeah.
I got 90. I also got 90 correct ones.
You got 90 correct ones, only 10 mistakes, but you got no mistakes from Lee.
Correct.
Got it.
Every time she didn't know, she said, I don't know. And so all of her unknowns count for 0 bits. But every one that she said yes or no, those were a full bit being transmitted because those were exactly correct every time in the channel. So, okay. So she gets a score for 90, whereas Steve gets a score of 53.1. Okay, so we've done some computing of the mutual information, or the amount of information being transmitted through the channel. And it depends on the structure of the uncertainty, the structure of the channel. We focused mostly on the symmetric channel, but we've also talked about the binary erasure channel. And there are many other kinds of channels that can be talked about as well. We're not going to talk a lot about them right now. We're going to talk a little bit more about redundancy. So that test was a thought experiment. I can pretend in truth. Have a different idea for our test situation. Suppose I don't have a erasure channel, but I simply use a symmetric channel, and the assumption here is that it'll be sent through a very noisy system. Any text character has a 50% chance of being lost and replaced by an asterisk. That is, in essence, unknown. So the lead scientist on the experiment wants to send his army of graduate students at the lab and order. Unfortunately, the channel is very noisy, and each text character has a 50% chance of being lost and replaced by an asterisk. So the lead scientist sends the message 5 times using the same noisy channel each time, just to be sure. So the resulting, well, 4 of the 5, the 5th one is underneath. But you can see that as you you can start that the first word is start. The second one is phase. The third one is to, of, experiment, A131. So because it's, even though it's got a 50% chance of losing every character, you still can read, and if you had the 5th one shown, you'd also see it. But you can, using 5 times of the 5 copies of the noisy system, you can figure out exactly what it says. No single message can be read, but when you compare all of the original messages, the meaning becomes clear. As I said, start phase 2 of experiment A137. Therefore, it appears that we can reduce the overall probability of error if I'm willing to send out messages redundantly. In effect, I send a longer message, and different parts of that message help me correct errors in the other parts. So no part of the message is immune from error. There's always a chance that I could make a mistake anyway. We could have all of the numbers on A137 be completely obliterated, and we wouldn't know what the answer was. So it improves the likelihood that I'll get the message right, but I could still make a mistake, even though I had sent it 5 times. So that improvement, of course, comes at a cost. if I use the channel many times, obviously the amount of resources is fixed and it slows down my communication. So to be even sure and avoid more error, it seems that I must have even more redundancy. Does that mean I need to repeat the message even more times? That might take quite a while, and there's got to be some inescapable trade-off between the volume of information and the reliability of the information. So Claude Shannon thought very deeply about this problem, and he considered it to be the key issue in information theory. And of course, he solved it. His solution is quite profound and surprising. He started by asking, what's the greatest measure of information that a given communication channel can convey? And this maximum amount of information is, of course, the maximum mutual information of the channel, or whatever particular design the channel has. And you calculate it differently depending upon the channel. So that maximum mutual information is called the capacity, or the channel capacity. So you define it as, you take the mutual information for all possible choices of the input and output messages, and you find the maximum mutual information, and that is the channel capacity. Now, we've calculated mutual information for the binary symmetric channel and for the binary erasure channel. And both of those, or the way in which they were calculated, are actually the maximum values for each channel. So we've already calculated their channel capacity. What Shannon proved mathematically was that as long as you don't try to exceed the capacity of your channel, you do not have to communicate more slowly to get rid of errors. So suppose I decide on an information rate R, a number of bits per time slice in the channel, constrained by the relationship that the rate of information is less than the channel capacity. By coding many messages together, which is called block coding, and by designing the right codes, which we're going to talk about next week, the right decoding procedure, we can achieve two different results simultaneously. One, sending an amount of information R each time I use the channel will make the overall probability of error go to 0 as long as we use larger and larger blocks in our code. So by stacking results together and using an appropriate coding mechanism, as long as the rate at which we can acceptably stand the bits coming down the channel, and that rate is less than the channel capacity, we can use a combination of the block length, the design of the code, and the decoding process. And if we do that, as we make our blocks larger and larger, the error will go to 0. Shannon also showed that if I get greedy and try to send too many bits each time, more than the channel capacity C, then over the long run, the error probability will go to 1. So you're gonna make consistent errors over time if you exceed the channel capacity. So the channel capacity is the key to understanding whether or not you're successful in your communication. Okay,
Quick question.
sure.
But could you go back to the previous slide? When you say coding, where you said coding many messages together, I guess it's the one right before this.
This one?
By coding many messages together, do you mean the same message multiple times?
No.
Okay.
I mean, you have multiple messages that you're going to send, and you use a coding for those messages, and then you stack them one on each other. So you make what's called a block code. So you take one individual symbol and it's coded, and it can be decoded. And by designing that code, both the creation code and the right decoding procedure, you can correct for many errors.
So you're not error correcting based on sending multiple messages, as you in that previous example. This is a totally different approach to sending multiple messages.
Right. So by coding the messages differently, that can decode also, and you stack them together. So now the blocking part is that you take, instead of just sending one message each time, you stack a bunch of them together.
Okay,
and,
good.
And that way, the structure of the coding and decoding procedure can take that into information in its design, so that the code you put together knows a priori how many blocks of symbols are going to be together. So you make a combination of information about the individual codes and the block of codes. So there's two parts in the process.
Thank you.
Sure.
Could I ask a little more about that?
Sure.
I wanted to ask you about both block coding and channel capacity. When you're saying stacking, are you stacking the same data over and over again, or are you stacking different data?
I'm stacking different data, but I'm choosing the number of symbols in a block each time. So I've got a code that I've designed that I can decode, but I also know the information of how many symbols will be put together and sent as a block. So let's say I did 100 symbols each time. So there'd be a code for each letter and a decoding procedure. And that information would also use the fact that we're going to put 100 symbols together every time. So we're using a combination of individual symbol codes and the fact that these codes are going to be stocked together 100 at a time. And the fact that you have that extra information allows you to get more information out in the decoding process.
So I do have one question, which is, in his derivations, does Shannon assume that the blocking is perfect? That is, if our agreement is 100 symbols, it's always 100 symbols, and there's never sometimes 99 and sometimes 103?
Yeah, that is exactly the way in which you deal with it. And in particular, you if you have a message that runs out of one, then there is always a padding symbol which you can use to fill out the rest of the block.
But
And-
the mathematics assume that you have some transmission technology that assures that you can detect the beginning and end of 100 symbol message.
Prado, come on. I'm sorry. I got a dog in my lap.
The
Okay,
brains behind the outfit, huh?
sorry. Yes, the assumption is that you're going to be able to grab 100 symbols each time.
So I can see how this would allow you to ascertain whether you dropped a symbol or added a spurious symbol. Offhand, I can't see how that tells you you got the wrong symbol.
Well, we'll use symbols with more bits. So an example is what's called a Hamming code. And you use a 3-bit symbol for a 2-bit result. And by knowing the structure of, you can either, you got 4 possible answers and 8 possible transmissions. So it's over specified. And because of the fact that the structure is used to measure these, you can use the 3-bit codes to decode the 2 code as long as there's only 1 bit of error.
Okay.
So we'll get to that next week.
All right.
I want to finish a little bit on what we've been doing about the theory right now. We're going to move into the application next.
Channel capacity.
Yeah.
What determines channel capacity? Is that the actual physical, fiber optic cable of, what size it is, how many little fibers are going through it? What is that?
Well, all channels are, described by probability distributions. So, yes, initially you need to know the information about the how it's made, what the type of error is, etc. But ultimately, a channel is simply a probability distribution. The model is a probability distribution because all you want to know in order to be able to determine the channel capacity is the maximum mutual information. And the mutual information only depends on the probabilities. So, because if you remember, we have the channel capacity, you take the mutual information, you look over all possible combinations of inputs and outputs, and you find the value of the mutual information that is the largest out of all those possibilities. And that is the channel capacity. So because the mutual information is only about the probability distributions, you always have to design the structure of a communication channel and model it as a probability distribution. So ultimately, you have to be getting into the kind of thing that we've been talking about in the symmetric channel with error, or the erasure channel. But however you calculate the mutual information, you need to know a description of how everything transmits through the channel, from the probabilities of the inputs and the probabilities of the outputs, and the nature of the information errors in the steps going between the communication channel. So it's always about a model in terms of a probability distribution.
I understand what you're saying. However,
So, Bob, am I right in saying that this insight of Shannon's was the reason that we all started to encounter commonly something called PK-zip or zip, where basically files were compressed drastically sometimes because the original information was not very close to the channel capacity, and so it was pretty easy to maximize it and therefore reduce the number of messages you really needed?
Yeah, that's a good part of it, yes. As long as you can, you know, in particular, the zip process initially focused on the text information being sent in ASCII. And ASCII is an 8-bit per character code. And obviously, if you are only dealing with the, you know, less than 200 symbols that are on a teletype or a typewriter or a computer keyboard, there's 2 to the 8th possibilities. There's obviously a lot of redundancy in the structure of the ASCII communication. And so they started, there's many kinds of condensing that is done. One of them is very different from the PK-zip. And this is where you give a symbol, and then you give a number that tells you how many times the letter is repeated. And if you choose the structure of that and limit the number of possible repeats, you can get a lot of reduction that way. So yes, the channel capacity tells you, as long as you are able to get the mutual information from point A to point B in less than the communication capacity, the channel capacity, you'll be able to reproduce the results that you put in. Okay, so yeah, I talked about this. Okay, so this result is called Shannon's second fundamental theorem. And many people think that it was actually the birth of modern information theory, not just the first theorem of entropy that Shannon came up with, and channel design. Anyway, Shannon's second fundamental theorem tells me that I can defeat noise without paying too high a price. There's no inescapable trade-off between information volume and information reliability. I can do error correction efficiently. The channel capacity tells us how efficiently. For instance, let's take the binary symmetric with error probability 1/10. We've done this over and over again. So the capacity of that channel is 0.531 bits. So as long as I choose a rate less than that, for instance, 0.5 bits per time is a convenient number. So to send 1 bit, I need to send the channel twice. Now I won't send the same one twice each time. What I'll probably do is take the 1,000 bits and send them twice, so I get 2,000 copies of it. And there may be, in addition, some complicated coding and decoding procedure, but there is a way that we'll talk about next week that'll allow us to give an overall probability of error. That is, that 1 bit error is made anywhere in the 1,000-bit message, negligibly small. This is, of course, assuming the 0.9, the probability of no error, or 0.1 probability of error. So there's a real lesson here, and the world is full of imperfections. When I calculate, I make mistakes over and over and over again. When I try to remember, I forget, but these facts don't need to have us go to despair. The science of information through Shannon's second fundamental theorem tells us that if we're careful and we are really smart about how we use our information channels, that error can be conquered. So I want to do a couple more things just before we move on to error coding. And the first thing I want to do is talk about the Kullback-Leibler distance. It's called distance, but it's not a distance that we would normally call in physics. That is, it doesn't use a metric. So you can think of it rather as a utility measure as in economics, or some separation between probability distributions. It is really a score that can be used to determine the mutual information of a channel. That's the reason we're talking about it. It is a score of how one probability distribution is different from a second probability distribution. So one is considered a reference, and then the other is a score which tells how different the two are. So we're going to deal again only with discrete probability distributions. So we have the same message space X, and we have two discrete probability distributions, P and Q, and they're of course on the same message space. And the Kullback-Leibler divergence from Q to P is defined to be the sum over all messages, X, of, now Q is going to be our reference. So it's the ratio of the probability of x to q of x multiplied by that probability. So it's very much like a entropy, but it doesn't use the QP on the log. So what you have to do is expand. First of all, you can invert it by using a minus sign. And then you can, of course, because log of A divided by B is log of A minus log of B. So it looks like entropy, except that instead of using Q of X log Q and P of X log P, we have P of X on both of those. So that is the measure of the distance between Q to P. So let's do an example, because I find that seeing the symbols doesn't usually do it very well for us. So let's have two discrete distributions, and they'll each have the same possible messages, 0, 1, or 2. And the pictures are shown on the right. So P is a binomial distribution with 4 and n equals 2. So we have 0.36, 0.48, and 0.16 as the outcomes. On the other one, the reference is a uniform distribution. That is 0, 1, and 2 all have probability 1/3. So if we calculate the tail divergence, we have the sum of the P of X, and I'm using log base E here, so that the answers are not in bits, but in nats or nits. Both are used. So there are bits, there are nibbles, which are base 3. There are nats, which are base E, and I forget, there's names for all of these different bases of the logs in order to measure the quantities in various kinds of, quote, bits, unquote. So we have 0.36 divided by 0.33, and the log of that, and multiply by 0.36, and similarly for 0.48 divided by that, plus 0.16 divided by that. When you do all that, you wind up and you get 0.085, roughly 0.1 nats of distance between the distribution of P and the distribution of Q. So P is over here, Q is here. Obviously, they're not the same. If they were all identical, all of the ratios would be 1, and hence the logs would all be 0, and hence the distance would be 0. So if they were identical, they'd have 0 distance, which is one of the things we want to see in a distance. This one shows that there's roughly 0.1 nats of distance from the uniform distribution. Now we can do it in reverse. We can switch the distance from Q to P. and we do the calculation all over again. And at the level of roughly 0.1, they're the same, but obviously they're not exactly the same, 0.085 and 0.097. So the KL distance is not symmetric. And that is not surprising due to the fact that Q of X and P of X are used in different ways for the calculation. In the one case, you've got Q of X on the outside of the logs, and in the other, you have P of X on the outside of the logs. So it's not symmetric. In information theory, the KL distance is also called the relative entropy of P with respect to Q. And in the context of coding theory, we're going to come back to that again, you can consider this to be a measure of the expected number of extra bits required to code the sample from P using a code optimized for Q. So this is a way of, if you have if you are Bayesian, then obviously you start with a prior based on your experience, and then as you learn more, you change that probability distribution. So the distance, you may have initially thought you knew what Q was, but turns out P is more accurate. So if you had designed the codes based on your prior, then you would need to know the DL, the KL distance, number of extra bits in order to get the samples from the updated probability P using the codes customized for the prior Q. So this is this is the relative entropy of the probability P with respect to Q. The mutual information can be defined in terms of the KL divergence. You take the joint probability distribution and you measure the distance between the joint distribution from the two marginal distributions. So if you considered the joint probability distribution model of a channel, you could look at and find the marginal probabilities. Now, in statistics, almost always people do what's called IID, identical independent samples. And that means that the assumption is that P of X and P of Y are independent. So they're simply the product of P of X times P of Y. The fact that you know it is not that, the mutual information, the availability that could come out of the channel is the distance, is the KL distance or divergence of the joint probability distribution and the product of the two marginal distributions. The joint distribution can always be, and remember that these parallel lines essentially means inside the KL divergence, you're taking a log of the two terms here in the parallel lines, you're taking a log of the ratio of those things. Now, the joint probability distribution, P of xy, is always equal to P of x times P of y given P of x. That's an identity. So if you put that in, obviously, you can take the KL distance between P of y given x divided by P of y, because the P of xy becomes P of x times P of y given x, and you're dividing it by the 2, so the P of x's drop out, and you just have the P of y given x relative to P of y. And of course, you have to sum over all of the appropriate elements of the message collection. And in this case, you have to do it over the x's. And the same thing goes the opposite way. You can always change P of xy into P of x given y times P of y. And then, of course, the P of y's will drop out in the ratio, and you wind up with the P of x given y and P of x, and then you have to sum over the probabilities of all the y's. So there's a real, the mutual information is often defined in terms of the tail divergence. When you see people talking about it, this is what we're doing here. Okay, so as I said, you have the independent products and you have the joint probability distribution. So you must need more bits to give that additional information that isn't in the independence assumption of px times p of y. So you must have more bits, and that is what the mutual information does, is it tells you if you had a completely independent set of outputs, the mutual information, the amount of information being communicated across the channel is due to the fact that the probability distribution across the two messages are different from independent. Okay. So I hope that we've accomplished a lot. I've discussed about Shannon's primary information tool, the entropy. We've talked about communication channels, and we've used two specific designs, the symmetric channel with error and the binary erasure channel with no error. The mutual information describes the relationship between the input terminals and the output terminals, the transmitter and the receiver, and the importance in redundant symbols to reduce the error rate, the channel capacity, which limits the transmission rate. As long as you can transmit the information you want less than the channel capacity, you can design it so as to have the error be as small as you'd like. The KL distance its use is in correcting errors in transmission, and we'll talk about that more next week. So I'll finish up with the error correcting codes and any other thing we need from information to understand information from for thermodynamics. And then I'll move on to Maxwell's Demon, the Slazard engine, Hamilton flows, Ito states, and finally to describe thermodynamics in terms of Shannon information theory. So any questions about today's material?
I don't have a question, but I did find Shannon's 1948 paper on the internet. I forget, you know, the full paper is like available somewhere.
Right. It's not a big paper. It's I don't know, 60 pages or something like that. I strongly recommend that you read it. Okay, assuming that everybody's happy with where we are, I'm gonna, oh, my timing was good. It's 12 o'clock.
Well done. Very enjoyable. I now have to go back and figure out how to pass this class, though, because I failed, I guess.
Well, you really got to know exactly what you know and what you don't know. That was the difference of the explanation.
I was wondering, I thought back to them when they would tell you about some of the ways exams are corrected, some of these standardized exams, the advantage of guessing when you're not sure or answering when you're very sure. I wondered how that played into this. I
don't know. I have seen those discussions as well, and I haven't. It's been so long since I saw them. I can't see whether or not those were informationally useful, and of course they depend upon how the scoring system is used within the standardized questions. I was using simply entropy as mutual information as the score in the tests that I was talking about. And I was just simply trying to make a point that if you have uniform uncertainty about every answer, the results that you get are quite different from an information theory point of view than if you actually know the same average number of questions and the rest you just simply do not know, and you announce that you know exactly the right answers, and you know exactly when you don't know the answers. That changes the information flow in the channel quite distinctly.
Yeah, very much so. Thank you. Very well done again today. Enjoyed it a bunch.
Great. Okay. Well, I'm going to, let's stop the share.
Okay, thanks.
Sure, then let me stop the